Hi, my name is Javier Morlana, and I'm going to present you my work ColonMapper, topological mapping and localization for colonoscopy. Our goal is to achieve mapping and localization in colonoscopies, a domain characterized by typical challenges such as surgical tools, fluids, illumination changes, and deformations. Several works in the literature have tried to obtain 3D maps of colonoscopy images, which typically results in small disjoint 3D maps. They are unable to obtain a global map that can be used later. There are two different approaches to obtain maps from a sequence. The first one is to obtain a metric map, running several steps like image matching, geometric verification, and incremental 3D reconstruction. The outcome of this approach is a 3D point cloud that encodes the 3D position of the elements observed in the scene and the camera position relative to them. This is the approach used by typical SLAM or structure from motion algorithms. A different approach is to obtain a topological map. Here, images are aggregated by covisibility, where two images are covisible if they are observed in the same place. The 3D estimation is avoided, obtaining a map composed by nodes and edges, where edges can model traversability or covisibility between nodes. We choose the topological approach for building our system ColonMapper. ColonMapper operates in two steps. Firstly, it builds a linear topological map from a mapping sequence, aggregating covisible images into nodes. The result is a topological map that will be used later to localize another sequence of the same patient. We localize through Bayesian localization, being able to detect previously visited places, for example, polyps that could not be removed in the first visit. Going more into detail, let's start with the mapping stage. For example, we will build a topological map with the withdrawal phase of sequence 27 in the EndoMapper dataset. We build nodes by aggregating covisible images. The current node is inserted into the topological map if at least it contains 3 covisible images. Otherwise, we discard the node to avoid the insertion in the map of unuseful frames like walls and fluids. We are able to build a topological map, covering the whole colon, being the first work in the literature able to process a full global map from a full colonoscopy video. Later, this map will be used to localize another sequence of the same patient. But first, we need to talk about how do we find covisibility between images. Our mapping is powered by deep features that enable covisibility estimation. We employ a neural network to extract a global descriptor. The network is trained for image retrieval in the EndoMapper dataset, being able to give high score for images depicting the same place and low scores for images depicting different places. This is used in the mapping stage, but also will be used in the localization stage. We also use an off-the-cell lofter, a transformer-based image matching algorithm able to yield semi-dense matches. We deem an image pair as covisible if lofter finds more than 100 matches. We build nodes by grouping covisible images. Starting from a current map, we initialize a node with an image and a descriptor. Then we keep processing the sequence, skipping images that are too similar based on the global descriptor similarity. When an image is different enough, we run a lofter matching step, adding this image to the node if it is successful. We keep adding images to the node until lofter fails to find covisibility. Then the node is closed and added to the map, and a new node is started. Once the map is built, we will use it to localize a different sequence from the same patient. In this example, we will use the withdrawal stage of sequence 35, a second exploration to the same patient of sequence 27 performed 2 weeks later. We use a Bayesian filtering approach for our localization algorithm. For every image in the localization sequence, we estimate the probability of being localized in the nodes of the topological map previously built. Here you can see some details about our localization pipeline. On top, we see the topological map, weighted by the localization probabilities of the current frame in sequence 35. We can also see an approximate location, in this case the ascending colon, and also the localization results based on our labels. On the bottom, we can see the reject node used to reject the spurious observation that hinders correct localization, such as walls and fluids. Our localization algorithm gives a probability estimation for every image in the sequence, but only selects a node localization once it is above a threshold, avoiding a lot of false positives. We are able to localize along the entire colon in real time, achieving high precision and recall. Our system is able to locate images of the same patient taken within 2 weeks of each other, which is useful for real-world disease monitoring use cases. As mentioned, we use a classical Bayesian filtering approach. Colonoscopy priors are encoded in the time evolution model, while the likelihood is obtained by comparing global descriptors. We evaluate our approach in the ColonMapper dataset, showing the benefits of our trained models and the Bayesian localization. We evaluate in the 3 cases displayed. In the first case, we observe that the entry map is not good enough to localize, as the doctors tend to go as fast as possible to reach the thecum, having less visibility than withdrawal stages. Our trained models and the Bayesian approach boost performance in the later cases, showing that place recognition is doable for second visits. These are some localization examples. While ColonMapper gives a few broad localizations due to extremely similar appearance, it is able to localize with high precision along the entire colon. We have shown ColonMapper, the first system able to create a global map of the whole colon that is used to localize previously visited places even in different sequences of the same patient. We believe ColonMapper can be really helpful for real-world disease monitoring use cases. Thanks for listening. Check our GitHub if you want to know more.